Inter-process communication, IPC. Have you ever heard about inter-process communication in operating systems? Of course you will ask yourself, what is the need for the process to communicate? Surprisingly, it turned out not only the human can communicate, so does the processes, but what is this exactly means? For better understanding, let's understand the two types of process. First, independent processes are those can neither affect other processes or be affected by other processes. Meaning there is no shared state between process, memory, file system. An example, an isolated program that calculates factorial sequence. Only input alone determines the output. Second, cooperating processes are those that can affect or be affected by other processes. Two programs sharing a single terminal. You want to print some document, you must have it on some editor. The printer needs to work along with the editor to make the document printed for you. So we can say, it's a mechanism allows processes to communicate with each other and synchronize their actions. The communication between them can be seen as a method of cooperation between them, which is done through both shared memory, message passing. Back to the question, there are many reasons, but we will be discussing information sharing as we saw in the printer example. Computation speed-up, a solution to a problem can be found faster if the problem can be broken down into subtasks to be solved simultaneously. Modularity, which is the most efficient architecture to break a system down into cooperating modules. And we will see explanations and seek for your understanding. In computation speedup, if we want a particular task to run faster, we should break it into subtasks, each of which will be running in parallel with the others to perform the same task. In modularity, dividing the system functions into separate processes. This is similar to what Cinderella's friends are doing. They divided the functions into separate processes as shown in the video. Every one of them is doing a different function. Another topic we need to understand first is buffer. Is an area in the main memory that is used to store or hold the data temporarily that is being transmitted either between two devices or between a device. In simple words, buffer temporarily stores data that is being transmitted from one place to another. There are three types of buffering that we'll be discussing generously. First, zero capacity, bounded buffer, unbounded buffer.
Have you ever went to a bank and waited in queue lines before? In buffering, messages are passed via queues, same as customers in bank waiting for their service. To understand buffering, imagine you are in a bank and waiting in queue lines to take a bank service. In this example, messages are represented by those who are waiting in queue lines. Messages are passed via queues, which may have one of three capacity configurations. In zero capacity, the queue's maximum capacity is 0. Messages cannot be stored in the queue, so senders must block until receivers accept the messages. Hence, messages can't wait in the queue until a process receives the message. So in this case, if the process wants to make sure that the receiver gets the message, the sender has to wait until the receiver gets the message. Now let us talk about bounded buffer. A bounded buffer is one with a finite capacity. You can only buffer a certain amount of elements in it. Senders must block if the queue is full, until space becomes available in the queue, but may be either blocking or non-blocking otherwise. When there is no more space left to store the elements, the producer threads putting the elements wait for someone to consume some of the elements. On the other hand, the consumer threads cannot take elements from an empty buffer. In such cases, the consumer thread will need to wait for someone to insert elements into the buffer.
The last type of buffer is unbounded buffer, which is the queue has a theoretically infinite capacity, so senders are never forced to block. Now let's talk about the two mechanisms we mentioned earlier, that are used by the processes to communicate, starting with the shared memory mechanism. Process A and B wish to communicate in shared memory mechanism. The responsibility for the kernel is to set the memory to be shared between the two processes. After that, kernel can go. Now process A can write the message to B via write function. After process A finish writing, process B can read the message via read function. Note that process A and B cannot write at the same time. This will cause an overwrite situation.
In this example, process A wants to send a message to process B and vice versa. Process A requests for a communication. Here the kernel is needed only to establish the connection between the processes and set the memory, which is the mailbox. On the other hand, the user is responsible for the communication. Shared memory is faster once it is set up because no system calls are required and access occurs at normal memory speeds. However, it is more complicated to set up and does not work as well across multiple computers. Shared memory is generally preferable when large amounts of information must be shared quickly on the same computer.
Process synchronization was introduced to handle problems that arose while multiple process executions. It is the task phenomenon of coordinating the execution of processes in such a way that no two processes can have access to the same shared data and resources. The data is passed via an intermediary buffer, which may be either unbounded or bounded. One of the classic problems of synchronization is the producer-consumer. It has two main actors, the producer and the consumer. In the following scenario, we will understand the general idea of the producer-consumer problem. John is the best chef making burgers, but he has only one plate that of a limited size that will fit for 6 burgers only. John made the burgers and placed them on the plate one after another. After doing all of these burgers, John felt tired, and he fell asleep. He went to sleep mode. His head accidentally falls on the bell. When Bob heard the bell, he knew that food is ready. He ate all the burgers. After eating all of the burgers, he felt tired and sleepy. So John was the producer and Bob is the consumer. The plate is the bounded buffer, it has a limited size. The producer will produce the data. After finishing, he must go into sleep mode to let the consumer know that it's his turn to consuming the data. After finishing, he must go into sleep mode too, to let the producer know he can produce new data. Process A wishes to communicate with Process B in message passing mechanism. The kernel will take the responsibility for passing the message to Process B. Kernel will send the message via send function, and deliver it to Process B. Process B will receive the message via receiver function, vice versa.
In this example, Process A wants to send a message to Process B and vice versa. Note that there is no direct communication between the two processes. If any of the processes wants to send a message to the other process, it should be passed to the kernel first. Here Process A is the sender and Process B is the receiver. As we know, message passing requires system calls for every message transfer. So as we see here, it is the kernel's responsibility to deliver the message to the other process. Now Process B is the sender and Process A is the receiver. This process will continue until no more messages will be delivered. Therefore it is time-consuming. But it is simpler to set up and works well across multiple computers. Message passing is generally preferable when the amount or frequency of data transfers is small.
In this video we covered types of process, reasons why the process become a cooperating process, what is inter-process communication, what is the buffer and types of buffer, the synchronization problem, the methods that are used by the process to communicate. Thanks for watching.